ever wonder how an airplane wing or a massive bridge can handle these incredible forces without just snapping? Well, the secret is all about the invisible stresses hidden deep inside the material. Today, we're diving into a core engineering concept called stress transformation. It's basically the method engineers use to hunt down a material's single weakest point and then design everything around it to make sure it never, ever fails.
Just look at something like these turbine blades. I mean, they're spinning thousands of times a minute, dealing with insane heat and pressure. You've got forces pulling them, shearing them, twisting them, all at the same time. So if you're the engineer, what's the number one question you have to answer? It's this. Out of every single microscopic point on this blade, where is the most vulnerable spot?
You'd probably think that at any tiny point inside that metal, the stress is just one number, right? A certain amount of push or pull. But what if I told you that's not the whole story? The truth is actually way more fascinating, and it's the absolute key to designing things that keep us safe.
So how can stress not be a single value? Well, it all comes down to your point of view. Seriously, it's a problem of perspective. Now, to make this whole thing easier to wrap our heads around, engineers simplify the problem a bit. They use a concept called plane stress. Instead of thinking about all three dimensions, we just focus on a really thin, flat, 2D slice of the material. And honestly, for things like beams or the skin of an airplane, that's where most of the important stuff is happening anyway. So here it is, the big idea, the pushing, the pulling, and the sliding forces that you'd measure at one single point inside a material, they completely change depending on the angle you choose to look at it from. It's the exact same point in space, but a different perspective reveals a totally different reality of the forces at play. And this slide shows it perfectly. On the left, you've got our standard, straight-on view of the stresses on a tiny little square of material. But on the right, all we've done is rotate our viewpoint and bam! Look at that! The forces are completely different. These new forces are the transformed stresses, and they tell us what the material is really feeling at that exact same spot. Okay, so how do engineers actually figure this out? How do they know what the stress looks like from some other angle? Well, they do this little thought experiment. It's almost like a forensic investigation deep inside the material. What they do is imagine slicing that tiny square element open, creating this little wedge shape. Now, they already know the forces acting on the flat original sides. So just by using basic physics, the idea that all the forces have to balance each other out, they can mathematically solve for the exact forces that must be acting on that new angled face. Pretty clever, right? Now, you can imagine that doing that whole wedge analysis for every single possible angle would take forever. So engineers came up with a much more powerful tool. You can think of it like a secret code or a formula that instantly translates stress from one point of view to another. Yeah, instead of drawing endless diagrams and doing that slow, manual slice and solve method, we can use a set of general equations. It's a direct path that does all the heavy lifting for us. And here they are. These are the stress transformation equations. Now, don't worry, you don't need to memorize these. The important part is what they do. You just plug in the stresses you already know from your straight-on view, you plug in whatever angle you want to look at, and these equations spit out the brand new stresses for that perspective. It's basically a universal translator for stress. And all of this brings us to the real reason we do any of this. All this theory, all this math. It's not just some academic exercise. It's about finding the hidden dangers. It's about finding those specific angles where the material is under the greatest possible threat. That's the whole point. An engineer uses those equations to scan through every single possible angle at a point, just to find the absolute worst-case scenario. Where is the pull the strongest? Where is the sliding force the most intense? Because that's the spot where failure is going to start. And they're really hunting for two specific danger zones. First, what we call principal stresses. These are the angles where the pulling or pushing force is at its absolute peak. And what's wild is that at this exact angle, all the sliding force just disappears. It's zero. Then they look for the maximum shear stress. This is the angle where the material is trying its hardest to tear or slide apart. This is what that principal stress state looks like. See how clean that is? The element is perfectly aligned so that there are only pure push and pull forces on it. There is absolutely zero shear. This is the angle where a brittle material, like glass or concrete, is most likely to just snap. And here's the other critical state, maximum shear. This is all about those sliding forces. This is the orientation where a ductile material, something like steel, might begin to stretch and deform. And you'll notice there's still a normal push/pull force acting here too.
And what's really amazing is that these two critical angles aren't just random. The orientation for the maximum sliding force is always exactly 45 degrees away from the orientation for the maximum pulling force. They are fundamentally locked together. Okay, so let's bring this all home. Why does any of this analysis actually matter in the real world? It matters because it lets engineers see a failure before it ever happens, and that lets them design things that are fundamentally safe for all of us. Take a look at this concrete beam. It's been loaded up in a lab until it cracked. Now, it might just look like a simple break, but the angle of that crack, it's telling us a very, very specific story. So why that angle? Why did it crack along that specific diagonal line and not, say, straight up and down? The answer is everything we've just been talking about. And here's the payoff. Concrete is great when you squeeze it, but it's terrible when you try to pull it apart. It has very low tensile strength. That crack followed the exact path where that pulling force was at its absolute maximum. It cracked right along the direction of the principal stress. Using those transformation equations, an engineer could have predicted the precise angle of this failure before the test even started. So the next time you cross a bridge or you fly in a plane, just remember that its safety is no accident. It's the result of engineers understanding these invisible shifting stresses, finding that absolute worst-case scenario, and designing to make sure it never happens. So the real question is, what other hidden forces are being managed all around you, keeping you safe every single day?